Now come to the nature of carbon-halogen bond. The halogen atoms are more electronegative than carbon. Therefore, carbon-halogen bond of alkyl halide is polarized. The carbon atom bears a partial positive charge, whereas the halogen atom bears a partial negative charge. As you see here in the diagram of haloalkane. Here carbon carries delta positive charge while halogen carries delta negative charge. As we go down in the group, in the periodic table, the size of halogen atom increases. Fluorine is the smallest and iodine atom is the largest. Consequently, the carbon-halogen bond length also increases from carbon-fluorine and carbon-iodine. Some typical bond length, bond enthalpies and dipole moments are given in the table 6.2. So let's try to understand it. Here this is carbon and there is bond between some halogen. This carbon has already made bond with another 3 hydrogens. The carbon-halogen bond is formed by the sharing of electrons. Here there are 2 electrons. Carbon belongs to 14th group and halogen belongs to 17th group. Here this is carbon and here this is fluorine, chlorine, bromine and iodine. When you go across the period, what happened to the size? Size of atom decreases. As the size of atom decreases, electronegativity increases. And electronegativity is the tendency of an element to pull the shared pair of electrons towards itself. So halogens are more electronegative than carbon. That's why they shared this shared pair of electron towards itself. And that's why the carbon-halogen bond becomes polarized in nature. And as a result of it, halogen develops partial negative charge and carbon develops partial positive charge. Now when you compare the bond length of carbon-fluorine, carbon-chlorine, carbon-bromine and carbon-iodine. What is the bond length? First try to understand it. Bond length is the distance between two nuclei. This distance is the bond length. This is bond length. Shorter the bonds are stronger and longer bonds are weaker. So you can say bond length is inversely proportional to the bond enthalpy. This is bond enthalpy. Bond enthalpy means the energy required to break a bond. Shorter bonds are difficult to break. If bond is shorter, it is difficult to break, means shorter bond has higher bond enthalpy. And longer bonds have lower bond enthalpy. Longer bonds have lesser bond enthalpy. Now let's compare the bond length of carbon-fluorine, carbon-fluorine, carbon-bromine and carbon-iodine bond. Here carbon is common, but when you compare between fluorine, chlorine, bromine and iodine, when you go down in a group, the size of atom increases, and bond length is the distance between two nuclei. So when you compare between carbon and fluorine, they both are smaller atom. So the bond length will be smaller. When you compare between carbon and chlorine, chlorine is bigger. So the distance between carbon and nucleus of chlorine will be more than the carbon and fluorine. So the bond length of carbon-chlorine will be more than the bond length of carbon-fluorine. So we can write when you compare the bond length of carbon fluorine, carbon chlorine, carbon bromine and carbon iodine, bond length increases. So we can write here bond length increases. And as we have discussed, bond length are inversely proportional to the bond enthalpy. So when you compare between them, you will see bond length increases, that's why bond enthalpy decreases. And we discussed earlier that when you go down in a group, electronegativity decreases. As the size of atom increases, you can write here electronegativity decreases. As electronegativity decreases, the pull of electron will be less in case of iodine and pull of electron will be more in case of fluorine. So the dipole moment will decrease. Dipole moment will decrease when you compare between carbon fluorine, carbon chlorine, carbon bromine and carbon iodine. I can write in this way also, carbon fluorine, the bond length will be more in case of carbon chlorine and it will be more in case of carbon bromine and it is most in case of carbon iodine. This is the bond length. When you compare between bond enthalpy, this trend will be reverse because longer bonds are easier to break. When you compare between the electronegativity, you know fluorine is the most electronegative one. That's why when you compare between the dipole of carbon halogen bond, you will see this will be carbon fluorine will be more polar than carbon chlorine and then carbon bromine and carbon iodine. Now come to the next point. Alkyl halides are best prepared from the alcohol, which are easily accessible. Today we are going to learn about methods of preparation of haloalkanes from alcohol. So let's read from the book. The hydroxyl group of an alcohol is replaced by halogen on reaction with concentrated halogen acid, phosphorus halide or thionyl chloride. So here these are the reaction. First reaction is given with HCl and alcohol. Second reaction is given with phosphorus halide. It is PX3. And the third reaction is given with SOCl2 with alcohol. So let's study each one by one. First of all, we are going to study the reaction of alcohol with halogen acid. Here this is alcohol ROH. When it reacts with haloacid HX, OH group of alcohol is replaced with halogen and as a result of it alkyl halide is formed. So RX is formed along with the formation of water molecule. So first of all we are going to learn about the preparation of chloroalkane. How chloroalkane is formed by the alcohol. So let's take an example of any alcohol. We can take the example of propanol. So it is CH3 single bond CH2 single bond CH2 and this is OH. So this is propanol. When it reacts with HCl, as we want to prepare chloroalkane, that's why we have taken HCl. So when it reacts, here chlorine will replace OH. I am not going to discuss the mechanism. I am just going to discuss what are the preparation methods. When we discuss alcohol, at that time I will tell you how this reaction take place. So here When OH is replaced with Cl, you will get the product CH3, CH2, CH2 and Cl. So this is chloropropane. Along with the formation of water molecule. Let's read from the book. Here it is given that reaction of primary and secondary alcohol with HCl requires the presence of catalyst ZnCl2. With tertiary alcohol, reaction is conducted by simply shaking the alcohol with concentrated HCl at room temperature. As we have discussed in the first lecture of haloalkane, how to classify haloalkane in primary, secondary and tertiary. In the same way, you can classify alcohol also in primary. So this is primary alcohol, secondary alcohol and this is tertiary alcohol. So let's take one example of each. Primary alcohol means this is the carbon to which OH group, that is your functional group, is bonded. It should attach to the one more carbon. So it is attached with another carbon. Now balance the hydrogens. So here it is CH3, this is CH2 and this is OH. Secondary alcohol means the carbon to which your functional group OH is bonded. It should bond it to another two carbons. So here this is one carbon and this is another carbon. Now balance the hydrogens. So here CH3, here also CH3 and here is H. So this alcohol is secondary alcohol. In case of tertiary alcohol, the carbon to which functional group is bonded to another three carbons. So here it is bonded to another three carbons. Now balance the hydrogen. So here CH3, CH3 and this is also CH3. As it is written in the book that primary alcohol when it reacts with HCl. So let's write the reaction with HCl. This is HCl. When it reacts with HCl, it requires catalyst. Secondary alcohol also require catalyst and tertiary alcohol doesn't require any catalyst. Primary alcohol require catalyst ZnCl2. Secondary alcohol also require catalyst ZnCl2. While your tertiary alcohol just requires shaking at room temperature. So at room temperature, this reaction take place. So here you will get the product. You can write the product. You just have to replace OH with Cl. CH3, CH2, Cl. Here also you can write the product. You just have to replace OH with Cl. Everywhere you just have to replace OH with Cl. Here also we just have replaced OH with Cl. So when you replace OH with Cl, you will get your product. So here it is CH3, CH, Cl, here CH3. Write down the product. In tertiary alcohol, here CH3 and here in place of OH you can write Cl. This is also CH3. So that's how this reaction take place. Now let's read from the book. Here it is written that the order of reactivity of alcohol with a given haloacid is tertiary, secondary and primary. Because tertiary alcohol react with HCl without any catalyst and just at room temperature. That's why it is more reactive. So tertiary alcohol is more reactive than secondary than primary. So this is the reactivity order of alcohol. Reactivity order of alcohol. Primary alcohol react least, then secondary, and tertiary react the most. Here we have discussed the formation of chloroalkane. Now we are going to discuss the formation of bromoalkane. So let's write the heading of bromoalkane. So how do we prepare bromoalkane? From alcohol. For the preparation of bromoalkane, we are going to use HBr in place of HCl. So here this is alcohol. When it reacts with HBr, you will get bromoalkane. Now let's read from the book. Here it is written that the constant boiling with HBr is used for preparing alkyl bromide. For the preparation of alkyl bromide or bromoalkane, you just need to boil the alcohol with HBr. Let's read from the book. Here one equation is given. Here this is ROH plus NaBr plus H2SO4. It gives RBr plus NaHSO4 plus H2O. So for the preparation of alkyl bromide, another method is also given in which ROH means alcohol when it reacts with sodium salt of bromide. So NaBr is taken in presence of strong acid. Strong acid is H2SO4. The role of H2SO4 is to remove this OH. So as a result of it, you will get RBr. Byproduct will be NaHSO4 and H2O. So what is the role of H2SO4? The role of H2SO4 to remove this OH easily. That we are going to discuss when we discuss alcohol chapter. Let's read from the book. The preparation of alkyl chloride is carried out either by passing dry chlorine gas through the solution of alcohol or heating the mixture of alcohol with concentrated aqueous halogen acid. Now come to the preparation of alkyl iodide. Or iodoalkane. For the preparation of alkyl iodide or iodoalkane, you cannot simply heat alcohol with HI. You cannot heat simply alcohol with HI. So for the preparation of alkyl iodide, different method is given. So let's read from the book. Here it is given. This is the reaction for alkyl iodide, for the preparation of alkyl iodide. To prepare alkyl iodide, you have to heat alcohol with red phosphorus and with iodine. In that case, you will get alkyl iodide. And let's write the reaction. So here this is ROH, which is your alcohol, and here it is to be heated in presence of red phosphorus. So here this is red phosphorus in presence of I2. So because it is heated with I2, OH will be replaced with I. Here you have to replace this OH with I, and you will get the product alkyl iodide. Here RI is formed and OH will be removed with the phosphorus. Now for the preparation of alkyl bromide also, you can use the same reaction. For alkyl bromide also, we can write the same reaction. For the preparation of alkyl bromide, you can take ROH and you have to heat it with red phosphorus with Br2. When Br2 is heated with red phosphorus and with alcohol, Br replaces OH, and here you will get the product alkyl bromide. So here you will get RBr. So this is another method for the preparation of alkyl bromide. Now let's discuss the reaction of alcohol with phosphorus halide. So here the reaction is given with phosphorus halide is ROH when react with PCl5 or when it react with PX3, it gives RX or you can say RCl. So let's discuss the reaction with phosphorus trihalide and phosphorus pentahalide. Reaction with phosphorus trihalide. So here reaction with phosphorus trihalide. When phosphorus trihalide react with alcohol. So here this is ROH. When it react with phosphorus trihalide, here X will replace OH. So here you will get RX, and here byproducts are important for your exam point of view. In case of phosphorus trihalide, 3 moles of alcohol are required, and as a result of it 3 moles of alkyl halide are formed along with H3PO3. Here X can be chlorine or it can be bromine. So here you can take PCl3 or you can even take PBr. When alcohol react with phosphorus trichloride, so here you can write any alcohol, you can write here CH3 CH2OH. This is ethanol. When it react with PCl3, you will get 3 moles. Here also 3 moles of alcohol are required, and here you will get 3 moles of CH3 CH2 Cl, means chloroethane is formed along with the formation of H3PO. Similarly, you can write the reaction with PBr3. So here again 3 moles of ethanol we can take as for example. So here CH3 single bond CH2 OH. When it react with PBr3, you will get 3 moles of CH3 CH2 Br, and H3PO3 is formed as a byproduct. Now come to the reaction with phosphorus pentachloride. So here is the reaction with phosphorus pentachloride. Reaction with phosphorus pentachloride means PCl. So let's write the general reaction first. This is ROH when it react with PCl5. Cl will replace OH. So here you will get RCl, and here byproducts are POCl3 and HCl. Now write the specific reaction. We can take the example of again ethanol. So here this is CH3 CH2OH when it react with PCl5. So Cl will replace OH and you will get CH3 CH2 Cl, and byproducts will be POCl3 and HCl. Now let's read from the book. So let's read from the book. Phosphorus tribromide and triiodide are usually generated in situ, means they are produced inside the reaction mixture only, by the reaction of red phosphorus and bromine and iodine respectively. Means the reaction that we have discussed here, ROH plus red phosphorus with X2 gives RX. So in this reaction, actually phosphorus tribromide and triiodide are formed. So here you can understand it. When phosphorus react with Br2, it generated PBr3. When phosphorus react with I2, it generates Pi3. So the reaction is nothing but the same as we just have discussed with alcohol and PX3. But the formation of PX3 in case of bromine and iodine take place inside the reaction mixture. That's why we have to take red phosphorus with Br2 or I. Now come to the next reaction in which we are going to discuss the reaction of alcohol with SOCl2, which is thionyl chloride. Here it is given with the thionyl chloride. So let's write the reaction with thionyl chloride. So here we are going to discuss the reaction of alcohol with thionyl chloride. Thionyl chloride is SOCl2. So let's write the general reaction first, then we are going to discuss the specific reaction. Here this is ROH. When it reacts with thionyl chloride SOCl2, it gives RCl, SO2 and HCl. SO2 is a gas and HCl also a gas. As these two are the gases, they escape from the reaction mixture and you will get pure alkyl chloride. Let's read from the book. Here it is given that the thionyl chloride is preferred because in the reaction alkyl halide is formed along with the gases SO2 and HCl. These two gaseous products are escapable. Hence the reaction gives pure alkyl halide. This is the best suited method for the preparation of haloalkane from alcohol. Now come to the next reaction. Here it is given the good yield of Ri may be obtained by heating alcohol with sodium or potassium iodide in 95% orthophosphoric acid. So now let's write the reaction. First of all, write the general reaction. So your general reaction will be ROH when it reacts with NaBr in presence of H3PO4. It gives RBr and the byproducts. Here byproducts are H2O and NaH2PO4. So now write the specific example. We can take ethanol. So here I can write C2H5OH when it reacts with KBr, or you can take NaBr. So here I have taken NaBr with orthophosphoric acid H3PO4. It gives bromoethane C2H5Br and you will get byproduct NaH2PO4 and H2O. Now let's read from the book. The preparation of alkyl chloride is carried out either by passing dry hydrogen gas through a solution of alcohol or by heating a mixture of alcohol and concentrated aqueous halogen acid. Here it is written that the above methods are not applicable for the preparation of aryl halide because carbon-oxygen bond in phenol has a partial double bond character and it is difficult to break, being stronger than a single. So let's try to understand it. In case of alcohol, this is the example CH3 single bond OH. Here the bond between carbon and oxygen is a single bond. Single bond means longer bond and it is easier to break. While in case of phenol, here this is the benzene ring in which single and double bonds are in alternate position, and here is oxygen and this is H. In case of oxygen, there are two lone pairs. When these two lone pairs delocalize, over the benzene ring. This double bond moves to the carbon in the form of negative charge. So when you draw the another resonating structure that you have learned in the 11th standard, these two bonds remain same and the double bond move to the another carbon in the form of negative charge. So here it will move to the another carbon in the form of negative charge and the carbon-oxygen bond become double and oxygen develop positive charge. So because of this partial double bond character, it is very difficult to break the bond between carbon and oxygen in case of phenol. Because being double bond, this bond is shorter and shorter bonds are stronger. So that's why the bond between carbon and oxygen cannot be broken in case of phenol. That's why you cannot substitute OH group with a halogen. While in case of alcohol, the bond between carbon and oxygen is a single bond which can be easily broken and OH can be substituted by the halogen. So that's why the reaction that we have discussed cannot be used for the preparation of aryl halide. Now come to the reaction of preparation of aryl halide from hydrocarbons. So let's read from the book. From alkenes by free radical halogenation. Free radical halogenation that you have discussed from alkenes by free radical halogenation that you have learned in 11th standard. Free radical chlorination or bromination of alkane gives a complex mixture of isomeric mono or polyhaloalkane, which is difficult to separate as a pure compound. Consequently, the yield of any single compound is low. This reaction takes place in presence of UV light. So here this takes place in presence of UV light or heat. When this reaction takes place, variety of compounds are formed and the yield of any single product is very low. Because chlorine can replace any of the hydrogen present in the molecule. Now come to the next reaction from alkenes. The addition of halogen halide and alkene is converted to corresponding alkyl halide by the reaction with halogen chloride, halogen bromide or halogen iodide. So here we are going to discuss the formation or the preparation of alkyl halide from alkene. With the reaction of halogen halide, means haloacids. So let's take an example. Here, this is the general example. Alkene means carbon-carbon double bond. And these are the other valencies of the carbon. When it reacts with HX, it forms C, single bond C. At any of the position, halogen can be attached. And rest of the positions will be satisfied by the hydrogens or any other compound. Now take the specific example. So here if I take the example of CH3 single bond C H double bond CH. So this is propene. When propene reacts with HCl, so by the reaction of propene with HCl, one of the bond between carbon and carbon double bond will break and H and Cl will get attached to the carbon, respective carbon. So this reaction takes place according to Markovnikov rule. This is MK rule. What is the MK rule? According to MK rule, negative part of the reagent goes to the carbon that is bonded to which is bonded to less number of hydrogen. So when you see here, which carbon is bonded to less number of hydrogen? This carbon is bonded to 2 hydrogen, while this carbon is bonded to just 1 hydrogen. So chlorine will get attached to the carbon which is bonded to less number of hydrogen. So here you will get the product CH3 single bond CH, single bond CH, and here Cl will get attached to the second carbon and H will get attached to the first carbon. So the name of this molecule will be 2-chloro-propane. This will be the major product of the reaction, while minor product will be 1-chloropropane. This all you have learned in the 11th standard. Now let's read from the book. The addition of halogen halide and alkene is converted to corresponding alkyl halide by the reaction with halogen chloride, halogen bromide and halogen iodide. Means the same reaction can be performed with HBr, Hi, and it is also performed with HCl that we just have learned. Propene yields 2 products, however only one predominate as per Markovnikov rule that you have learned in 11th standard. Now come to the addition of halogen. In the laboratory, addition of bromine in CCl4 to an alkene resulting in discharge of reddish brown color of bromine constitute an important method for the detection of double bond in a molecule. So this method can be used for the preparation of alkyl bromide and as well as for the detection of unsaturation in the molecule. So let's understand the reaction. In this reaction, we can take the example of ethane. This is C double bond C and all the valencies are satisfied by the hydrogen. Means the molecule is ethene. When it reacts with Br2 in the medium of CCl, Br2 is brown colored compound. So this is brown color. When it reacts with the alkene or the molecule in which unsaturation is present, unsaturated molecule give the addition reaction when it reacts with bromine. So as a result of it, C single bond C, here CH2, here is CH2. Now bromine get attached to both the carbons. Here bromine get attached to both the carbons. When it get attached to both the carbons, the color of bromine get discharged. So that's why this reaction can be used for the detection of unsaturation. Detection of unsaturation in the molecule. In this reaction, brown color of bromine get discharged. Due to addition reaction. Due to addition reaction. In this reaction, vicinal dihalide is formed. Vicinal dibromide. Vicinal dibromide means the functional group bonded to the adjacent position. Adjacent position is the vicinal position. Now let's solve this question. Identify all the possible monochlorostructured isomers expected to be formed on free radical monochlorination of CH3 whole twice CH, CH2, CH3. To solve this question, first of all, draw the structure of the given molecule. So the molecule is given C, H3 and it is bonded to CH. There are two CH3. Then this CH is bonded to another CH. CH is bonded to CH2, single bond CH. So in case of monochlorination, you have to replace hydrogen with chlorine. So here you have to replace H with Cl. So identify how many types of hydrogens are there. So these are the primary hydrogens, this hydrogen, this and this hydrogen. So we can replace these hydrogens with Cl. And the other type, this hydrogen is the secondary hydrogen that can be replaced. And one more hydrogen is there. This one is the tertiary hydrogen that we can replace. So that's how you will be able to draw the structure of structural isomers formed by the monochlorination of this given molecule. So first of all, you can draw the first structure. This is CH3, single bond CH. Here it is CH3, single bond CH2. This is CH2 because we are going to replace one of the hydrogen with chlorine. So this is the first structure isomer. Now draw the another structure isomer. Here it is CH3, CH, single bond CH3. This is CH, single bond CH3. So this time we are going to replace this hydrogen with chlorine. So this will be the second structure isomer formed by the monochlorination of the given molecule. Now we can draw another structure. So this is CH3, C, CH3, CH2. This is CH3. So this time we are going to replace tertiary hydrogen with chlorine. So this will be the third structure isomer. Now let's draw the next structure. So here this time we can replace one of the hydrogen of CH3. CH3, this CH3. Here I can write CH2 and now I am going to replace one of the hydrogen with chlorine. So this will be the fourth structure isomer. If I want to replace this hydrogen with chlorine, I will get the same structure. So let's try to draw the same structure. CH2 single bond CH, this is CH3, CH2, this is CH3. If I replace this hydrogen with Cl, I will get this structure. Now to convince yourself that both the structures are identical structure, write down the IUPAC name of both the molecules. So first of all, select the longest carbon chain that includes your functional group Cl. So here this is the longest carbon chain that includes functional group Cl. So it is 4 carbon long chain. For here also you can select the longest carbon chain. So this is again 4 carbon long chain. Now number the chain so that functional group chlorine gets the lowest possible number. So I can number the chain from here. This is 1, 2, 3 and 4. Here also I can number from here 1, 2, 3 and this is 4. So chlorine gets the first number and this substituent, this is methyl substituent, get the second number in both the cases. So when you write the name of first molecule, you will write 1 chloro, 2 methyl butane. In the second case also you will get the same name 1 chloro, 2 methyl butane. As they both have same IUPAC name, means they both are the identical structure. So there are only 4 structured isomers formed by the monochlorination of the given molecule. Now come to the next reaction. This is halogen exchange reaction. So first of all, read from the book. Alkyl iodides are often prepared by the reaction of alkyl chlorides or bromide with NaI in dry acetone. This reaction is known as Finkelstein reaction. Here the reaction is given Rx plus NaI. When it reacts, Ri and NaX is formed. X can be chlorine and bromine. So let's write the reaction. This is Finkelstein reaction. This is Finkelstein reaction. It is for the preparation of alkyl iodide or for the preparation of alkyl iodide. Alkyl iodide from alkyl bromide or alkyl chloride. So let's write the reaction. First, this is RCl or it may be RBr. When it reacts with NaI, here also you can do the same reaction with NaI in acetone. So acetone is the reaction medium. Here also acetone is the reaction medium. So in this reaction what happened? Cl and I get exchanged together. Here Br and I get exchanged together. So as a result of it, Ri is formed and NaCl is formed. And here again Ri is formed and NaBr is formed. This NaCl and NaBr, they get precipitate in acetone because they are insoluble in acetone. NaCl and NaBr, they are insoluble in acetone. That's why they get precipitated. As you have learned in the chemical equilibrium chapter of 11th standard. Because NaCl and NaBr will be removed in the form of precipitate. That's why it favors forward reaction. According to Le-Chatelier principle. So let's read from the book. NaCl and NaBr thus formed is precipitated in dry acetone. It facilitates forward reaction according to Le-Chatelier principle. The synthesis of alkyl fluoride is best accomplished by heating an alkyl chloride and alkyl bromide in presence of metallic fluoride, such as AgF, Ag2F2, COF2 or SbF3. This reaction is termed as sword reaction. In this reaction, here methyl bromide is taken with AgF. During the reaction, F and Br get exchanged together and as a result of it, fluoroalkane is formed. This is fluoromethane along with the formation of AgBr. So here you have to remember these fluorides which can be react with alkyl bromide for the formation of alkyl fluoride. These are AgF, Ag2F2, COF2 and SbF3. This reaction is called as sword reaction. So Finkelstein reaction is for the preparation of alkyl iodide, while sword reaction is for the preparation of the alkyl fluoride. In the next class, we are going to discuss the preparation of haloarenes.